Okay, so I'm recording. Now, this first video
Dude, guys,
that
my
we
intro
have
was
here,
better than the
Gabriel.
ebook. Epic.
So our first thing right here is we're looking at two magnets getting close to each other. As you can see, one of them's obviously right here. This one's the predator. As it goes towards its prey, it unfortunately is unattractive towards its prey because we have
because it is ugly.
opposite magnetic poles. With magnets, we have like our north and south poles, whereas with electric fields, we had our positive and our negative. And as you can see, it has captured its prey because it has its south pole over here, which would be generally the negative pole, and then its north pole over here, which would be the positive pole, and it causes attraction. Which is something.
Magnetic stuff today?
Yes, which is something I believe you all have learned previously in elementary school.
The north pole of a magnet is pushed toward the...
Stop audio. And then alternatively, you have them when they're both the same pole, causing repulsion and sort of pushing each other away, so that way that prey gets to escape and survive to fight another day. So, in the video of the interacting magnets, consider how the magnet on the left is moved as the magnet on the right approached. Did the forces of the magnet change as they got closer together? So, as they got closer together, did the force change?
The closer they get,
Get
The closer they get.
exponentially more pushy a party.
Yeah,
The south pole of a magnet...
I thought I said audio off, child.
There's one picture for class color day.
Alright, so...
Do you have any purple object? Oh, can I have these?
Yes, as they get closer together, the forces sort of increase. So it works similarly to the way that the forces of electric fields and sort of point charges work it's a similar fashion. They're an inverse square law when it comes to magnetic force, just like it was when for electric fields, so positive and negative charges. So, with this one, where we sort of are magnetizing things, which we're not going to do because I don't think you have magnets at home.
I do.
Oh, you do? Okay, well, if you have magnets and if you have sewing needles, you can actually do this thing where you make your own personal compass by rubbing the needle on the magnet, or the magnet on the needle, and then you float it in a cup of water, and you have yourself your own personal compass. Bill Nye has done this in his videos. I am not going to do it in mine because I don't have magnets.
But it's not true north.
It's magnetic north.
Yeah.
Alright.
I need to always do that whenever I get lost.
Well, you need magnets and you need a cup of water
So I'll bring that.
and a
Get
needle.
gyroscope with a magnet in it.
You at that point you might as well just bring a compass.
Hey. Dan, gyroscope with magnet.
But what if it's like emergency?
Gyroscope.
Like say.
If it's an emergency, you should have still brought a compass.
But no. Like what if I lost my compass?
Gyroscope.
What if you
When
then?
I was
Why do you
lost.
expect that you would have kept the magnet and the needle and the cup of water? If you lost the compass, you lost everything important.
You can only need two.
So
like
the cup and the needle would be like a like.
Brain.
Wait.
All right. Anyways, so to sort of demonstrate how these electric fields work, and sort of like the idea of what would happen when you have your two. I forget words. Your two magnets near each other, and you wanted to sort of see what the magnetic field looks like. You can do a little experiment where you shake out iron filings all over and sort of around, and as you shake them out, they'll find that they'll be magically arranged into sort of the form, into lines to demonstrate the electric field.
Spikes.
So, like, as you can sort of see, they get spiky towards the part because that's where the magnetic field is strongest, but as you can see, You do
It's just
have
like the
those
electric
those
fields.
lines, and it's sort of an arrangement where they're sort of making these magnetic field lines. And one thing to note is that it is actually three-dimensional, so if there wasn't this flat surface, you would actually have needles coming up and over the North Pole to the South Pole. But it's much easier to visualize it with iron filings on a flat surface, but as you can see here with the spiky boys, it's going in every direction. And also when you have gravity playing a part and sort of forcing it down, it does make it a little bit less significant in the vertical directions.
Then have you ever actually poured iron
Ta-da!
filings?
And look at that. Do some tapping on the paper, and bam. Strong looking magnetic field lines.
I've done that before.
Dan, how do we do this like activity thing?
What do you mean activity thing?
Like that you're looking at right now. See that?
So basically what you're going to be doing is, like, the idea is that you're doing what was just done in the video down here.
Oh, we're just.
Oh, you're just drawing lines.
Yeah,
Oh.
basically you're drawing
I
sort of
thought
the
you were talking
magnetic
about
field.
real time.
However,
Yeah.
however, with this one, like, what's the
It's in
difference
reverse.
between this and between this?
They're attracted.
Oh, they're attracted.
Yeah, so the fields would be going in between the north and south poles, rather than.
What about the one on the other side?
What about the one? So we might end up having something like this. It gets a little weird.
Yeah.
It works similar to electric fields, and then we'd have like a very bam, bulby.
Some of them go out, like into.
Yeah, they go all the way back around. There's this sort of paper stuff that you can get that you can put over a magnet, and then it has little bits of iron filings in it, so it shows up with with the fields.
Pretty cool, Gabriel.
Oh yeah, as well as if you ever have those things where you have the little magnet and you have the person's face and you sort of make them have a beard or hair.
What?
Yeah.
Wait.
Like those
Yeah.
little like dollar toys that you might have had when you were younger. Or maybe it's just me before technology.
Yeah, those are epic.
Why does it say due Wednesday?
So the original video I showed you was sort of with them both being north to north facing each other. This one is more of the type we have on this diagram, so we can sort of see a better effect of how it would look.
Attracting.
Yeah, attracting to each other.
So is this where are we supposed to do this? Is this in making magnets? I'm guessing.
Yes, it's in measuring magnetic force, not making magnets. So, like with it, let me scroll back some. With it, as you can see, so it works pretty similarly to the previous one, and it's so you have like the sort of similar to how I drew. You have the you have some of this going on, but you also have a lot of this and a lot of this. And the field lines don't cross, but basically you have I want to say crab claws just sort of popping up everywhere. It is all connected and just sort of loops back into itself repeatedly, kind of like a nice little wave pattern, unlike my drawing, which is not as good. Hey, they fixed the eraser. What do you know? Oh, and now there's more colors.
Oh, of the first page. I don't understand. I need to read.
So you'd have something like this, and then you would equally have lines coming out through there, although they wouldn't cross, just like electric field lines. And then boop. But you'd basically have this wide, sort of flowery looking thing like we have in the video, which is pretty cool. Now, with this, in the image, what image? Oh yeah, so in this, if we think about it, how these magnets would react if they were sort of, since they're separated, what do we expect to sort of happen between these two magnets? Do we expect them to attract or repel? Asking the audience. Yes, attracting.
Attract.
Yeah, we'd expect them to attract, so that would be the net force would be attractive. However, on both of these we have like south-south, north-north, but it's attractive because similar to our electric points, our electric fields, and our point charges, the forces between them, they obey the inverse square law, which basically means that the attraction of the two closest poles is far greater than the repulsion of the more distant poles.
Well done. Because the force
Is basically the big thing here. Like when we have two charges close to each other, their forces are pretty big, but as they get farther and farther away, less and less force between them. Now, if you place a compass on a level surface far away from any bar magnets or other laboratory sources of magnetic fields, the compass's needle will move and then stabilize. So with a compass, what is happening? What do we sort of expect is going on with the compass away from any magnets? What is it aligning itself to?
The poles of something.
Yeah, so the poles of the Earth's magnetic field, it sort of aligns itself to all that. So what it would end up happening is it would just it would align itself with the Earth magnetic field, so you'd have the needle pointing in the same direction as magnetic north and magnetic south, depending on which side is charged in what fashion. So like this, if you had it around a bar magnet, they'd be pointing along the same way as the magnetic field lines, which is kind of cool. And so that's sort of one of the big things. If you drew all the lines, you would have something that looks like this.
What do we do when we're done?
What do you do when you're done? You're good. You're good when you're done. And look at all these nice little magnet things.
Today we have an assignment and it's painful.
So, that is the majority, and then you'll go through, you'll finish some of these things.
What IXO?
And
Patricia,
then you'll be
it's Wednesday.
to go back and do next, and don't forget I'm
Info.
still recording.
Oh.
It's like the